In this video, we're going to show you the problem number 3.9. Number 3.9 is a problem which we're going to solve. So this is where the problem is all about. I hope you can read this part. And it's about, we assume the conducting sphere was grounded in the beginning, but now with additional second charge, and you can find out this also can handle case with a sphere with a finite v, so v not necessarily zero, and what charge should you use, where you should put it. Find a force attraction between point charge q and neutral conducting sphere. So these are multiple problems which is actually involved. So I'm going to show you the one at a time. Suppose I have a sphere like this, and outside this charge I normally call it Q1. This is a true charge, and you have something like this come out. Now we know that from the class, and we're going to place an image charge for the Q1 over here. That's Q2. Suppose this is the center, and so that's what we have. We don't know how large this is. Of course, we already calculated. Let's call it B. From the center to the charge, I think this is called A. Let me double check it. Yes, it's a from here to there is called A. That's what we have. Now, as I said, if this is connected with a non-zero potential, it's called V0, then we need to place another charge. Let's call it Q3. Q2 and Q3, these are image charges, not a real charge. The Q1 is a real charge. And then, so that's what we have. Let's assume that from the center sphere to the charge Q3, that's a C. From here to there, it's a C. I hope you can read them. So in other words, these two is the, from here to there, it's a C. That's what we have. Now, from the previous class, we knew that we can find out how large the Q2 is and how large the B is. So that's what we do. But this time, I want to show you really generic. In other words, we do not assume prior knowledge whether they are exact, same, or different. We don't care. So we're going to do systematically. Again, we're going to choose 2 points. One point is over here. Let's call it point A. And so we do it at a time. So we're going to do step number 1. First, we're going to choose point A. So that's a point A is about, and this is going to be the point A. And it has 3 contributions. One is charge Q1, has a contribution Q2 and Q3. So you will see my VA has 3 contributions with V1A, V2A, and V3As. So these are the 3 contributions. So then all I need to do is just write each of these terms down. V1A, the potential is just Q1, which is over here, divided by 4 pi epsilon 0. And then we need to find the distance between the charge Q1 to the point A. From here to there is R. From here to there is A. So this distance is just simply A minus R. V2A is similar. V2A, what we do, we have Q2, 4 pi epsilon 0, and this time is R minus B. So you can see from here to there is R. From here to there is B. So this distance is just R minus B. Let's look at the 3A's. We have Q3, which is over here, and then this A is over there, so which we have 4 pi epsilon 0. This time it's C plus R. Okay, C plus R. And so this is what we have. In principle, you can actually choose the move this the Q3 to the other side of the same thing, because the expression is similar in this particular fashion. Now it's time to take a look at how this works. So we're going to use the different knowledge about how to do the calculation. So the first knowledge, so the first note is that the initial potential from Q1 and Q2 adds up should equal 0. What that means is that V1A plus V2A is going to equal 0. And this is in the sense that assuming that the potential V0 is 0, so this is what we have. We use this third chart to recover this V0. There are small steps which is involved. So this is the first that you need to know. So from this one, we are able to find out an expression for the Q2. So now if this is 0, then my V3A has to equal V0. Okay. So in other words, we have this contribution V3A has to equal 0. Essentially, this terms here will be equals V0. So let me write this down. Q0 will be 4 pi epsilon 0 V0 C plus R. Let me highlight this. This allows us to get 0 potential at point A. So then the entire sphere, the conducting sphere on the surface will be equal to potential like this. And that's the very first term we need to do.